Hello, every professor. I'm Wang Zhuo. I'm studying at University Technique Mara. My paper's title is an improved random forest algorithm based on hierarchical clustering. Random forest method is an ensemble learning method. It introduced the method of randomly selecting features on the basis of bagging. Because it has strong classification ability and stability, it has many application cases in the fields of medicine, industry, and agriculture. However, when the feature dimension of the dataset is high and there are a large number of redundant features, random selection of features may lead to a decrease in the correlation between features and class variables. Moreover, the features randomly selected may have high redundancy, which reduce the quality of the random features subset and may result in a decrease in the convergence of the RF model and poor generalization ability, thereby affecting the accuracy of model prediction and moreover performance. Many scholars have conducted relevant research on this issue. Some techniques are too complex, leading to high computation costs. This may limit the feasibility and scalability of the method in the practical applications. Furthermore, most of the methods are mainly applicable to a certain field, and their suitability for other application fields has not been fully explored and validated. Therefore, the applicability of these methods may have certain limitations. This study proposed a hierarchical clustering-based RF optimization algorithm. This improved process optimizes the establishment of feature subsets, reduce the influence of unless useless and redundant features, increase the correlation between features and class variables, and improves the quality of feature subsets. It also proves the excellent performance of the algorithm in different neighborhoods and the datasets of different scholars. Therefore, this study provides new solutions and ideas for improving and optimizing related problems, and also provides a new perspective and direction for the prediction classification framework. The problem that this study aims to solve is how to reduce the influence of useless and redundant features on the model performance without removing redundant features, retaining the original feature information, and meeting the diversity of RF. The HCRF algorithm proposed in this study attempts to solve this problem. During the process of establishing feature subsets, the architecture of the HCRF algorithm is shown in Figure 1. In Figure 1, the HCRF algorithm has two main optimization paths. The first is the feature grouping, which is completed by the hierarchical clustering algorithm. The second is the feature subsets are randomly selected from the feature groups in proportion. The training samples are generated by the random sampling with the replacement for the dataset. This study used the hierarchical clustering algorithm to perform feature grouping operations. The flowchart of the feature clustering is shown in Figure 2. In this flowchart, the parameters that the hierarchical clustering algorithm needs to determine mainly include clustering method, the method of distance measurement, and the clustering number. The agglomerative clustering is selected. The distance measurement method used is the centroid distance. It is decided by the distance between the centroid of the two clusters. Among them, the centroid of the cluster is the average of all sample points, the average of the GINI coefficient of the features. After features are clustered, those features with similar classification capabilities are grouped into a cluster. Then the features are randomly sampled from each cluster in proportion. These features are more representative and unbiased. A decision tree is built using these features. The process is repeated until the RF reaches its predetermined size. The steps for feature proportion sampling are as follows. 1. All features are divided into several layers. 2. Based on the total number of features n and the number of features per layer ni, calculate the sampling ratio for each layer. 3. The number of features to be sampled for each layer is calculated as number, and the total number of the feature sample in all layers should be n. 4. Features are randomly sampled from each layer based on the determined number, and the result sample set certain a total of n features. As shown in Table 1, this experiment selected 7 different neighborhood and different score datasets from UCI. The experiment used 10 flow cross validation. The experiment compares the comprehensive performance of the SVM, CUT, RF, and HCRF. Accuracy, precision, recall, FE score, and return and running time were used as evaluation indicators. This experiment selected 2 parameters of RF for parameter tuning, namely n estimators and max depth. The parameter n estimators is the number of decision trees that are built by RF, and if the value is too small, it will result in insufficient training. If the value is too large, it will increase the computation complexity and lead to overfitting. The parameter max depth is the maximum depth of the decision tree. The parameter mean sample is set to 1, and the max feature is set to HCRF n features. The Figure 3 to 6 compare the accuracy, precision, recall, and FE score of the 4 models in 7 datasets. As shown in Figure 3, the accuracy of the HCRF is the highest value on 6 datasets, indicated the accuracy of the HCRF is higher than the other 3 models. Accuracy of HCRF is improved by 0.1% to 6.32% compared to SVM, and by 0.18% to 1.76% compared to HRF. In Figure 4-6, the procedure RF and FE score of HCRF have been improved to varying degrees with a similar trend. Therefore, it can be proved that the optimization method proposed in this study has improved the quality of the feature subset and improved the generalization ability and improved the accuracy and overall performance of RF. The experimental results have verified that the optimization process proposed is effective and has achieved the research objectives. The above results include small, medium, and high dimensional datasets, and HCRF has excellent performance on each dataset. Therefore, it can be proved that the HCRF is suitable for small, medium, and high dimensional datasets and has broad applicability. Table 3 shows the running time of the 4 models on the 7 datasets. Figure 7 shows the trend of the models' running time. It is easy to see that the running time of the HCRF is less than the of the RF. Also, the running time of HCRF is slightly longer than that of chart. It is because HCRF builds 100 charts, but the time does not increase by 100 times. This shows that HCRF has a higher advantage in terms of time complexity. Therefore, the HCRF algorithm also has a higher application value and can be applied in a wide range of fields. In response to the issue of correlation and redundancy among features, and the quality of randomly selected features in RF, this study optimized the RF and proposed an HCRF algorithm based on hierarchical clustering. The experimental results show that the accuracy of the HCRF is improved by 1.01% and 15.27% compared to the other 3 models. Among 6 datasets, the accuracy, precision, recall, and FE value of the HCRF are the highest for the 6 datasets, including the high dimensional dataset, period, and macromass. The HCRF require less time than the RF. Domains training is a significant advantage in time complexity. The experimental results prove that the HCRF achieves the predefined research objectives, reducing the influence of feature correlation and redundancy on the model, and improving the model's generalization ability. and overall performance in the future. Further research will explore refining the detail of clustering to achieve higher accuracy and improve time complexity, thereby enhancing its practical value. Thank you for listening. This is all my presentation.